Welcome back, all. All right, so today the first thing I wanted to go over, or the first thing I really wanted to start with, was just finishing up some reactions for sugars. And so one of the last reactions that we will be talking about, at least for sugars, is sodium periodate. Periodate. So in this case, it'll be just sodium, Na, and then periodate, which is going to be this part right here. Now, this will only react with something called a 1,2 diol. And what I mean by that is, okay, let's say I have two OHs right next to each other on some kind of molecule. Now, note, these OHs must be cis to each other in terms of stereochemistry. So they have to be both wedged or both dashed. Now, if I react this with sodium periodate, what I get is I actually cut this CC bond right in the middle right here, and I turn these OHs into C double bond O's. So in that case, this is what we get. We cut the CC bond in the middle, and then we turn those OHs into C double bond O. Okay, so how can we apply this to sugars? And I promise you that these are reactive to sugars. Well, let's say we have something like methyl glucose, right? I say methyl glucose because I'll put in a methyl group on the anomer, as well as on methyl galactose, where I'll just put a methyl on the galactose right now. Now, let's say I just take those molecules and I just react it with sodium periodate. So in this case, both cases. Okay, well, what's interesting about this is that there is no reaction, or at least very little product, when you react methyl glucose with sodium periodate, as compared to something like methyl galactose, where all of a sudden we get a new product where we do cleave some CC bond, specifically between carbon 4 and carbon 3 right over here, and then we turn those OHs into C double bond O's. So why is that? Now, that seems kind of weird, right? Mostly because, hey, like, we were supposed to have, like, these are axial and this is equatorial, and yet this reacts, whereas this one, there is no reaction. Well, one thing to look at is the actual stereochemistry of it. How is it actually oriented towards us? Well, looking at all the OHs in this molecule, for this first one, well, that's going to be dashed. So this will be going down. This one will be going up. This will be wedged. And then this one right here would be dashed, so going down. Now, going through each of the different carbons, all of them aren't cis. In fact, they're all trans to each other, despite them being all equatorial. As compared to methyl galactose, where in this case we have something, again, it's going to be going down, which would be dashed. In this case, this would be going up, which would be wedged. But in carbon 4, this is also going up, so this would also be wedged. And because stereochemically, these are both on the same side, well, this can react with NiO4 and break the CC bond and make the two OHs into C double bond O's. Okay. Now, let's look at an example of ribose, right? So the real question is, at least the question I'm asking here, is what are the products of D-ribopyranose? Okay, so that's something to look forward to, with sodium periodate. Now, before we get into it, let's just note that, okay, D-ribose is going to be our sugar. That's why I have it written here. And pyranose means six-membered ring. All right? Okay. So what can we tell? So how do we make that six-membered ring first before we even figure out how to actually react this with NaO4? Well, first off, let's actually count the number of carbons we have in this molecule. So we have 1, 2, 3, 4, 5. So carbon 5 is the last one. Okay, well, the thing is it makes a pyranose, so it must be a six-membered ring. So our sixth group on this ring will be this oxygen right here. Always going to be +1 of the carbons that you're going to and the oxygen. Okay, well, if I wanted to do that, right, and note this is D-ribose. Okay, well, in that case, we would react it all the way to this CC double bond O, and now we have to see which side of, or whether they're going up or down in this case. Well, because it's a D sugar and it's a pyranose, we first draw the regular skeleton of something like that. So drawing the chair structure, this is a regular chair structure for a D sugar. that's a six-membered ring. So in this case, I'll label this as carbon 1, 2, 3, 4, and 5, and then 6, right? So there's a six-membered ring, and in fact, it matches the blue numbers that we have on this side. But okay, so where would we orient all these OHs across here? Now, it turns out that the anomeric carbon, that will just be some kind of, that would be, in either case, somewhere over there. Something in this case that's just some anomeric. In fact, in this case, what we can find out is that all these OHs are all on the same side and they're all pointing to the right. If they're all pointing to the right, that means they all must be down or pointing down when we put them on the chair. So starting at carbon 2, we can put the first OH down like this. And then the next carbon 3, that's also down, so it's going to be axial down. And then on carbon 4, it's also going to be equatorial down. Okay, now let's figure out what our products would be if we react this with sodium periodate. Okay, well, if we take sodium periodate, well, okay, we would have to cut all of the bonds between all of the COHs with all the bonds of the COHs that are all cis to each other. Now, this looks kind of weird because, okay, so these are both cis to each other, but these are also both cis to each other. And so the thing about sodium iodate is, well, it doesn't choose, it actually does both in either case. And so how can we visualize that? Well, drawing the sugar again. So in this case, right here, where this will just have some anomeric carbon. Let me draw that line better. Okay, anomeric carbon, and then going back up. Now, here's where it starts getting weird, all right? So because this is the first cis bond right here, this OH on carbon 2, that will turn into a C double bond O. All right. Okay, now looking back on carbon 4, there is an OH over here. So that would also turn into C double bond O. Okay, well, we cut out carbon 3. So what's interesting is that carbon 3 will come out with a C double bond O on one side from this and carbon 2, and then another C double bond O on the other side, with this being from carbon 3 and 4. So labeling our carbons again, this will be 1, 2, 3, 4, and 5. Because of that, our products would be this dialdehyde right over here. And then the last product right here would be carbon dioxide or CO2 gas. So keep in mind how all of the OHs are oriented, as well as what can come out of it when you're doing these reactions.